arrived in time for the first morning session. We are expecting around 80, 90 participants altogether. Not everyone is here, but I'm sure all of them will arrive eventually. And one thing is, as you can see, this room is barely enough for the number of participants. So please leave your extra seat nearby if they are available. Other than that, well, we will announce some practical information as we get along. Right. Let me jump to the first morning session. We will have 2 lectures by Yael Shadmi, and the topic is on-shell methods for effective field theories.
Thank you. You can hear me, right? Great. So good morning, everyone. It's a great pleasure to be here. I love being in Korea, so I'm very happy to be here. And it's really nice to see you all, and it's nice to start the school. And so I'm going to talk about on-shell methods for effective field theories. And this is really sort of an invitation to contribute. There are many things that can be done in this area, and so that's essentially the main objective is going to be to sort of tell you what sorts of things have been done, and maybe get some idea for what's interesting for people to think about. And one thing that's really nice about the Amplitude series is that very gradually amplitudes are an on-shell method. Sorry. Trying without. Okay. Let's see, maybe this is a little better because, okay, this is better. So let's see. Okay. Not quite. So one thing that's really nice about the Amplitude series is that these methods are permeating into all sorts of areas of physics. And so you have amplitude methods being used from everywhere between gravity to QCD calculations at very high orders and sort of everything in between. And so in this series of lectures, I'm going to talk about EFTs, and specifically I'm going to bring you my perspective, which is the perspective of a BSM person. So we're going to talk about the standard model. We're going to talk about some questions beyond the standard model. And of course, this is reflecting my perspective on what are the interesting problems and where is there good chance to see new data and hopefully see answers to these problems. Okay, and the first thing I want to do is I want to start by some, so this is roughly the plan. Today I want to start from some introduction to the standard model, some questions beyond the standard model and EFTs, and we'll see several incarnations of EFTs. Then we'll talk about some amplitude basics. Where we're going to be very brief and just describe the minimal stuff that we're going to need. Then we'll talk about amplitude constructions of EFTs, which are going to be bottom-up. And then we'll talk about different versions of standard model EFTs. and about Higgsing at the amplitude level. And then we'll see how we are doing with time, but hopefully we'll have some time to talk about positivity and about the calculation of anomalous dimensions and running. So that's roughly the plan, and we'll see how things go. Okay, and of course, feel free to stop me with questions at any point. And this is going to be, we don't have a lot of time for this, so this is going to be obviously very, very coarse and brief in some areas. And the other thing I need to warn you about in advance is that it's very, very hard to do justice to the literature in this sort of lecture. So I'm basically not going to give any references. And if you're interested in where to read the original papers, just come and ask me. Okay, so with this, let's start. So I'm going to talk a little bit about the standard model. And I wrote it in full glory here on the board, so we don't need to waste too much time. And I guess one of the main things which I can say about my perspective as someone working on beyond the standard model mostly, is that when you try to tweak the standard model, you realize what an amazing theory it is. It's really amazing. Anytime you try to do something to it, there's at least one disaster happening, and usually more than one. So it's a very, very simple theory. I mean, I guess most of you have seen this, at least in some detail. Basically, everything is specified by the group theory, the fact that we have SU3, SU2 cross U1 gauge symmetry, these representations of the fermions, and then we can write down this Lagrangian. And this Lagrangian does contain quite a few parameters, but it's basically the theory of everything. It's the theory of everything that we've measured, except for gravity. Gravity is not in the picture, but otherwise, it's really amazing that something this simple can do this much. And if you think about open problems in the standard model, I think you've heard of them, or most of them to some extent. All of them are either of theoretical nature, and we'll talk more about at least one of them, or they have to do with something that is related to gravity. For example, the main observational problem we have with the standard model is dark matter. But everything we know about dark matter has to do with gravitational observations, basically. So with regard to everything that's been measured, this is the theory, and it works extremely well. Okay, so now we want to be a little more quantitative about this. And first of all, describe the big successes of the standard model, but also talk about at what level we really know that this is the Lagrangian of everything except gravity. Okay, so as we said, this is a very simple theory. From a theory point of view, we have the following thing. We know that we have SU3, SU2, cross U1 broken by the Higgs to SU2 to SU3 times U1 electromagnetism. The fermion content is anomaly free. And the requirement of Having no anomalies also means that we have charge quantization. That is, the electromagnetic charge is quantized because the hypercharge needs to be quantized. And we have a very minimal, the most minimal Higgs sector. So from the theory point of view, this is sort of the simplest thing you could write down. It's, you could imagine much more complicated Higgs sectors to break electroweak symmetry, but you just put in the simplest representation of SU2 cross U1 and SU2 doublet, and it does the job. So that's all very nice. Then we have a few other nice things that I want to mention. So just from these few theoretical inputs, if we write down the standard model Lagrangian that I just did at the renormalizable level, we have a few important things. First of all, we see that baryon number and lepton numbers are accidental symmetries. And that's really nice because that means that the proton is stable, something which we care about a lot. Then the other thing that we see is that flavor changing processes, so something that would change, for example, a B quark to a U quark, that's something that's only mediated by the W's. So it's only the gauge interactions, the fermion interactions with the W that's here, only these mediate flavor changing. So that's also very important because it means that flavor changing at tree level involves a change of EM charge. And the other thing that it says is that the only flavor changing, the only neutral processes so if we want to have any process in which flavor is changing, for example, something that involves a B quark going into an S quark, that only comes in at the loop level, and it involves specifically W loops. So that is also very good because that means that these sort of processes are suppressed, and that's what we observe in nature. So it's a very minimal set of assumptions, and some of the most important consequences of this set of assumptions is this fact, the fact that B and L are accidental symmetries, and that flavor changing only occurs through the W, and therefore flavor changing neutral processes are very suppressed. Okay, and then there's one other thing that I want to mention about the standard model, and that's something that we often take for granted, but it's not completely, it didn't need to be this way. And that's the fact that we can, if we want to, we can extrapolate to very high energies. Essentially all the way up to the Planck scale. And it didn't have to be this way. We could have had a theory in which when we look at the running of couplings, we hit some strong coupling early on, but that's not the case. The standard model couplings happen to be perturbative up to very high scale, so we can at least imagine that there's nothing between here and nothing new between the scales that we have probed so far and the Planck scale, or very close to the Planck scale. So that's something sort of non-trivial. Okay, so then when you think about this picture, the first thing you want to ask yourself is it really completely tested? I wrote this Lagrangian here. It has all these different couplings. So we want to see how well we tested all of these couplings. So that's what I want to do now, sort of quickly. So the first thing we can ask is whether all these couplings have been measured at this point. And the question is yes. And the answer is yes. All of them have been measured at this point. And of course, when I say all the couplings there, I should talk about the physical couplings only. So the gauge couplings, of course, are all physical. But then we have all these Yukawa couplings. So these matrices Y up, Y down, and YL are all 3 by 3 matrices, which describe the fermion masses. So these are many parameters. If you count parameters in the Yukawas, there are 3 Yukawas. Each one of them, as we said, is a 3 by 3 matrix. And these are complex numbers. So that's another 2. So that's a lot of parameters. But out of these parameters, not all of them are physical, because I can always take my, so I wrote Q, which is a U and a D. So let me call these UL and DL. So I can do a rotation where UL goes to some VL, UL, DL goes to VD. Let me call this one VL U, and this is VLD. So I can take this to VL DL, and I can also redefine the U's by VRU and the D's by VRD. And then if you think about the physical couplings here, let's just talk about the quark sector. So in the quark sector, all we have is we have 6 masses, and 3 mixing angles. So out of these, in the case of the quarks, if we just remove the quarks from the leptons from the story, we have altogether 36 parameters here. Out of these 36 parameters, only 9 are physical parameters. And the reason is that we did a field redefinition here and removed many of the unphysical parameters to remain with just the physical ones. This is a very trivial field redefinition. It's a linear field redefinition, but nonetheless, it tells us that not all parameters are physical, only a very small subset of them are physical. And of course, all these parameters are measured. Yeah?
What is VL and VR?
Excuse me?
What is VL and VR?
Sorry. I meant to say that I'm rotating these guys. Of course, in this case, I don't care about them. I'm sorry. That's not, that shouldn't have been there. I don't care about these guys. All I'm saying is that all I want to say is that the CKM matrix is given by VLU star times VLD. This is what I wanted to talk about. But essentially, I could, the point is that I can take any of our quark fields and rotate it to go to the mass basis. So this is going to the mass basis for all the quarks. And in this basis, we have the 6 masses and the 3 mixings. Okay. Good. I mean, I could leave them here, of course, those extra rotations that we have. We can also take, as I said before, U can go to V RU times U, and similarly, D could go to VRD times D, but these don't enter into the parameters that we measure. Okay, any more questions about this? I'm going to come back to the neutrinos. For now, I'm not going to talk about neutrinos. Yeah. Okay. Good. Now, of course, this field redefinition is something that we can do for the gauge bosons too. Here, we're implicitly choosing some basis of SU3 generators or SU2 generators, for example. But of course, we can do some change of basis and define the fields in a somewhat different way. But this is something that we don't care about because we're talking about an unbroken symmetry. Okay. So now that's the first question. The first question was, have we measured all these? Have we measured all of these couplings? And actually, there's something else that I want to talk about here, but we'll come back to that. The second question is, have we tested these couplings? So the second question is, have we tested the couplings? And for that, of course, we need more than one measurement. So we have one measurement, that's just the measurement of the parameter, and then we need at least another one to test whether our theory is a correct theory. So let's look at that. So basically, I want to sort of grade the standard model Lagrangian by how well we tested things. So things with 2 stars are going to be things that we tested in all relevant processes. And I'll explain in a second what I mean. And things with a single star are going to be things that we tested, but not in all relevant processes. And things with this are going to be things that we haven't tested. Now, when I'm talking about tests here, then of course, the real question is with what precision? What's the experimental precision of each one of these tests? So this is something that I'm not going to get into. I just want to indicate which part of the standard model we tested in different phenomena and which are not tested at all. And I'm not getting into the question of precision. Okay, so we can start with the strong interactions. So the strong interactions, of course, I'm mainly talking about the perturbative level because I'm talking about high energies, but the strong interactions are extremely, are very well tested. So this part of the Lagrangian the gluon interactions, for example, and then the gluon interactions with fermions. This part is essentially tested. And the reason why I'm saying it's tested very well is because we have many, many different processes that probe these. So for the strong interactions, we have quark and gluon scattering in different sorts of colliders. So PP, PP bar, E plus, E minus. All of these test the strong interactions in different processes. So for example, one of the first signs that we're really seeing this structure is the fact that we have a three gluon vertex, which you can see in E plus, E minus going to 3 jets. And so that's for example, that's for the strong interactions. Yeah. Excuse me? For gluon is something. Okay, so I mean, of course, ultimately the thing that you do is you calculate the standard model prediction for some scattering process, and this is something that you test very well in lots of different things and way beyond leading order. So we have very good precision there. Now, of course, for the gluon vertex coming from this part of the Lagrangian, essentially, we know that the gauge symmetry relates this 4 gluon vertex to the 3 gluon vertex. They have to come with exactly the same coupling. So this is not really an independent input that I need in the theory, but I could calculate things using Feynman diagrams in terms of this guy, and either way I do things, the calculation agrees with experiment. So that's how you know that the structure is correct. Okay. Now let's turn now to SU2 course U1. So here we're really talking about the weak interaction plus electromagnetism. So electromagnetism, of course, is on very good footing. There are many, many tests of the electroweak interactions. Mainly they're coming from fermion interactions. And then you can also ask about gauge boson interactions that are sensitive to this. And so, but that's already in the weak. So I'm going to leave out the EM. So the EM is very well tested in all of the fermion interactions. For the weak interaction, there is the part where the fermions are involved. So everything related to the weak interactions of fermions is also very well tested. So let me put this here. So that all is very well tested. And then we can talk also about the gauge boson self interactions. So things like WW, W gamma, WZ. And these are now tested at the LHC. So these are really tested for the first time at the LHC. And this is an ongoing process, but you're really starting to probe these. And you're really starting to probe this for the first time. Okay, so the last thing that remains is the Higgs sector. And so now I want to talk about the Higgs sector. And here we have this Higgs potential here. And this guy, or this part of the Lagrangian, is the piece that's not tested at all. This is the only piece that's not tested at all. And remember that those, the gauge boson self-couplings are something that the LHC is measuring now for the first time, really. And this part is something that we've measured but not tested. So let's see why that is. So let me expand the Higgs as follows. There's a Goldstone piece here, and then here I want to write it as 1 over square root of 2 v plus h of x plus I g0 of x. So I want to expand the Higgs around its VEV. And VH, if we expand the potential, we see that V is equal to minus mu squared over lambda, and MH is 1/2 lambda V squared. So the Goldstone boson are eaten by the W and the Z, and we remain with the physical Higgs, and the physical Higgs is this VEV and this mass. And then when we expand the potential further, we see that we have a cubic interaction of the Higgs, which is proportional to lambda times V. And we have a quartic interaction of the Higgs, which is proportional to lambda. So where is V measured? So maybe you guys know the answer. Where is V measured? How do we know the value of V? So in the standard model, in the normalization that I wrote before, we know that V equals roughly 246 GV. So where is that coming from?
Anything relevant to the GF perimeter.
Right, exactly. Very good. So we know that from Fermi, from G Fermi, the Fermi constant. We also know that from the W or Z mass. So for example, the W mass is 1/2 G2 times V. I actually want to write that down. Yeah, okay, let me write that down here. This is the W mass, this is the Z mass in the standard model. 1/2 G1 squared plus G2 squared V. And both of these masses are measured. MW is around 80 GeV. And MZ is 91 GeV. But actually, the first time that this V was measured, this parameter of the Higgs potential, was when people discovered beta decay in the 1890s, okay? Because that's exactly what enters in beta decay. So let's review that. So what's happening in beta decay, or actually inverse beta decay, doesn't matter very much for us. So we have a neutron going to a proton E minus and neutrino. And actually what's happening is that we have a d quark that's turning into a u quark, and here comes a w, and the w then decays to an E minus and a nu E. And so, first of all, this is the first flavor changing process, because we have a d quark changing into a u quark, and you see that charge has to change in the process because we're emitting a w, or not emitting, but there is a w involved. And what this thing is, this is the first EFT. This is sort of the origin of all effective field theories in our field. So this is the first time that we see an EFT. And what's happening here is that we have G2 here and G2 here. So we have an amplitude. We have an amplitude that's proportional to this W propagator. So there's a G2 squared divided by P squared minus MW squared here, where this is the momentum. But of course, this momentum is completely negligible. So this is just G2 squared over MW squared. And that's precisely G Fermi. And if I want to carry the expansion to higher orders, what we have here is G2 squared over MW squared times 1 minus P squared over MW squared plus higher powers of the momentum. So this is the first time that we're seeing an EFT. And we see what happens here because these energies, the energies involved in the process are so much smaller than the W mass. We can do this expansion, and to lowest order in P squared, we get this constant. So this is actually the first measurement of the Higgs potential. So let me put it here. And if we put in the rate for beta decay, then roughly speaking, this is proportional to GF squared, where GF is G2 squared over MW squared. And if I substitute in MW, which is written over there, then GF is 1 over square root of 2 times 1 over V squared. And indeed, as was mentioned here, the most precise measurement, so the best measurement of this V is coming from muon decay. And what's happening in muon decay is very similar to what we just had, what we have on the board over there. We have mu here, a W, and an electron and an electron neutrino. So it's a very similar process. It's exactly the same story, and that gives us the most precise measurement of V. Okay, so coming back to the Higgs potential, we measured V, and since we measured the Higgs mass, and the Higgs mass is 125 GeV, to a very good approximation, then we also measured lambda. So with the measurement of the Higgs mass, all the standard model parameters are measured. But as you see, this is a parameter that we haven't tested at all. So lambda is not tested. We have one measurement of lambda from the Higgs mass. In order to test the standard model predictions, we would need to also measure the Higgs cubic coupling and the Higgs quartic coupling. Both of these involve lambda. Okay, so that's a part of the theory that's not tested. Okay, questions about this? Okay. Now, this is not the only parameter that hasn't been tested yet. So there's another part of the theory that we need to talk about. So as we said, this is not tested. And then we also have this part. We have the Yukawa couplings or the fermion-Higgs couplings, and these get mixed results here. So as we said before, we tested all the, we measured all the fermion masses and mixings. So if I want to make this a little more precise, here there are two parts, right? There's the VEV part of the Higgs, and then there are the interactions with the physical Higgs, because I can expand the Higgs just like I did over there. So the parts that just involve the VEVs, those are very well tested because we have many, many tests of the fermion masses and mixings. But if we're talking about the fermion interactions with the Higgs, that part is not tested or not completely tested. And that's a very active area in the LHC experiment at this point. So the fermion-Higgs masses, so the fermion masses, as we said, these get 2 stars. They're very well tested in different processes. If we're talking about fermion Higgs couplings, these are tested for the heaviest fermions, for the top, the bottom, and the tau, and the mu. So these are the ones that we know. These are the ones that are tested. The rest are not. And the other thing that I guess I forgot to say is you can also ask about Higgs couplings to the W, the W and the Z, and these are also tested. And again, the LHC is testing these for the first time. Okay, so that concludes the sort of review of where we stand with parameters that appear in that Lagrangian. And as you see, some of them are, the weakest point is the Higgs potential, which is not tested yet. In other words, we don't know whether this simple potential that we wrote down is the end of the story or not. This is an open question. But now there's another piece that I want to talk about, and that's the piece of what we need to add to the standard model to describe all measured phenomena. So there are measured quantities. Quantities not in L standard model. And this is exactly the question we had before. And these are neutrino masses. So we say neutrino oscillations, and that implies neutrino masses. And what we measure is two mass differences that I can call delta M23 and delta M12, and three mixing angles. So this implies at least two non-zero masses. One of them can be zero, but two have to be non-zero and different. And in order to do, and that's just not described by the standard model Lagrangian. But the modification that you need is a very sort of minimal or innocent modification, which is to write this five-dimensional Weinberg operator Cij divided by something that I'll denote mu, Lith Ljth. And so this is the dimension 5 operator. It involves two lepton fields and two Higgses. And when the Higgs gets event, this gives us neutrino masses, which are, or it gives us a neutrino mass matrix, mu ij, which is this Cij v squared over mu. And if you need to get the measured neutrino masses, what you see is that mu has to be around 10 to the 14 GeV. So that's the value of that mass that's required to explain the observed neutrino masses. Okay. Now, here, for example, is a UV model that can do the job. All you need to do is add a right-handed neutrino. So here we have mu I, mu j, the Higgs, and here there's some mu r, where this is some new Yukawa that I'm calling y prime. I'm not going to put the generation index here, but this sort of structure will give you the five-dimension operator that we're interested in. Okay, so this is the second time that we see an EFT. And that's what we need to add to the standard model to explain neutrino masses. Okay, so whether or not we refer to this as new physics is something that's a bit, it's sort of different people will refer to it in different ways. We don't need to add any new fields to the standard model. And we have seen EFTs before. We saw the EFT describing the W interactions. So the idea of effective field theories is a very natural idea for us. And we know that for whenever we do physics, whenever we do some experiment, all we're really doing is to use some effective field theory, because there's the Lagrangian describing the theory, but there is the part of the Lagrangian that's relevant for the energies at which we're doing experiments. So with the exception of LHC experiments that are now probing the highest energies we've gotten to and that are described by the standard model, in most other experiments, we're using some effective theory. And so there's nothing radical about imagining that there is some sort of EFT here, and that we need to add this higher dimension operator to account for neutrino masses without adding any fields at light scales. So we've seen by now already two different occurrences or two different examples of effective field theories in the context of the standard model. And so it's something that's very natural to think about. So in one of them, so we saw already beta decay or muon decay. We now see neutrino masses as another example of an EFT. In the first sort of, in both of these instances, actually, the new scale is associated with the mass of some weakly interacting particle that we're integrating out. So we have, I forgot to say heavy. We have a new heavy particle. We can integrate it out. In the cases that we saw before, this was a tree level, but that's not always the case. We can also have EFTs where we integrate something out at the loop level, and we'll see an example in a second. But of course, we can also have a different possibility that's also familiar from the standard model. And that's where the new scale is actually a composite new scale or confinement scale. And we also have that in the standard model. And that's the essentially the theory of mesons and baryons below lambda QCD. So at very low scales, we have mesons and baryons, which are composite objects, and they describe physics. We can write an effective Lagrangian, either the chiral Lagrangian for the pions or something more complicated that describes the effects of QCD at very low energies, or the effects of the electromagnetic and weak interactions. And so this is one example. So we can have, there are instances of, there are effective field theories that we already see at the level of the standard model that correspond to either this or that. Here we saw EFTs at tree level or tree level effects of EFT. Let me give you another example, which is a loop level integrating out, where, for example, we have a flavor changing process with the B changing into an S. So this is B going to S gamma, where this is the W, and here in the loop we can have in principle the top, the charm, and the U. So this also corresponds to some higher dimension operator or amplitude that we would get by integrating out the W at the loop level. At energies, we're talking about the B here, which is decaying. I'm sorry, not B to S gamma, but E to, that would be very, very exciting, of course. It's not what I meant to say. These would be an electron and a neutrino. So this would be for example, be, to S an electron and a neutrino. Okay, B to S gamma would be, of course, a very similar process, but wait, what did I actually? I got myself a little confused. No, I did want to say B to S gamma. Sorry. I guess I'm a little jet lagged. Okay, so that's another instance of having some EFT process that's mediated at the loop level. Okay, so that concludes the sort of where we are at the experimental level in the standard model. And I think I have about 5 minutes. Okay, so let me go on for another 5 minutes. Okay, so as I said, there are many tests that remain to be done at the LHC. We still need to test the Higgs sector. There are many processes that we haven't confirmed at the LHC. But when we talk about testing, experimental test, there are two ways that we can actually test things. So one thing which is completely obvious is to just calculate. You calculate standard model predictions, and you compare to experiment. And we already talked about some examples of that. And of course, when we talk about QCD processes, for example, you calculate to very high precision. You have very high order calculations. But then there's another thing that you can do, which is to try to come up with alternatives and to constrain them. So let me give you one example of that in the context of QCD. So let's say that we want to test QCD. We want to see whether QCD is the correct theory. So we can just ask the question, what if we add a higher dimension term, which is of the following form? I can write a 3-gluon operator like this, which is the trace of 3 field strength. And then I can calculate the effects of this guy on some scattering process, and I can try to look for that. So that gives another way of testing our theory, is just to come up with some sort of alternative and look for it. And in this case, the game is sort of that you're trying to look for different structures. There are many structures that occur that QCD predicts in gluon scattering, and this would be an alternative to that. And this is another way in which EFTs are used. So here, what you're trying to do is try to look for this, and then set a lower bound on lambda. And this is a model independent and sort of agnostic way to look for effects beyond QCD. Okay. So the main message I try to convey here is that writing a Lagrangian is not enough. We need to understand whether the Lagrangian describes nature or not. And then the next thing that we're gonna talk about is the problems that are still open theory problems in the standard model, and why we want to think about physics beyond the standard model, especially in the context of the Higgs. Yeah. Excuse me? Yeah. No, this is completely unrelated. This is just, this is in the context of just gluon scattering, so unrelated to the Higgs. Okay? Here I'm just talking about, you know, one way to test QCD is to predict 2-jet, 3-jet, 4-jet production, but this is just another way to do this. More questions? Okay, so I guess we'll stop here and go on after the break.